Hello everyone. In this video, I will be demonstrating how to perform a structural analysis of a ribbed wing in Ansys Mechanical. In this demo, I'll be taking a pressure map generated from a CFD analysis in Ansys Fluent and applying it to the ribbed wing in order to predict the stresses and deformations in the structure. Here in the graphical window of Ansys Mechanical, you can see the geometry of the ribbed wing that we will be analyzing today. If I hide the outer skin of the wing, you can see the internal rib structure. Looking at the geometry branch of the outline tree, you can see that all of the parts are grouped under one component, meaning the topology between parts is shared. As a result, the mesh at the boundaries between the parts is shared, eliminating the need for contacts. If we go to Space Claim, we can see how the geometry is set up in order to share topology. Here we are in Ansys Space Claim, and you can see all of the bodies that we have are grouped under one component. Here it's called Wing 2. If we look at the properties of this component, you can see we have the Share Topology field set to Share, meaning the boundaries between all of these bodies will share a mesh once I bring them into Ansys Mechanical. If we want to verify where our connected edges are, we can come to the Workbench tab and hit this button here. And anywhere you see a blue edge will be a shared boundary between two parts. You can also force specific boundaries to share topology with the Force Share button, in case this is not recognized. And if you have any small gaps between boundaries, you can use the Extend tool in order to extend that surface up to the other one in order to connect them. Coming back to Ansys Mechanical, we can take a closer look at the mesh we have on this geometry. So I'm going to navigate to the mesh portion of the outline tree here. And you can see I'm only using global sizing controls in order to generate the mesh on this geometry here. So the only things I've changed here are I set a maximum element size of 1/2 inch, and I also have capture curvature set to yes with my curvature angle of 30 degrees. So this means that one element can only represent 30 degrees of a curved surface. That would be why you can see that I have a higher mesh density on the curved surface of the wing versus on the flatter parts of the wing. Taking a closer look at the mesh, you can see that my elements from one surface to the other line up, verifying that my shared topology is set up correctly and it's working as anticipated. Now that we've covered the geometry that we're looking at and the mesh on it, we will take a look at the boundary conditions and loads that we will apply to the wing. So currently all we have defined is this fixed support here. It's on the cut boundary of the wing here, so that will be fixed and not allowed to move. But now I want to apply my pressure load from my earlier Fluent analysis to this wing. To do that, I'm just going to come back to my Workbench project page here. And I'm just going to drag my solution cell onto my setup cell in my static structural analysis. And then I will have to refresh afterwards. Now that that's done, if I come back to my mechanical window here, you'll see I have this imported load folder here with a question mark next to it. The next thing I'll need to do is insert my pressure load here, and then I will scope it to whatever faces I want the pressure to be on. So I want to apply this pressure to all of the surfaces of the wing. And now I can just right-click and hit Import Load. Now that our pressures are done importing, we can take a closer look on the pressure we're applying to the wing. So you can see, based off of the contour plot here, we have lower pressures on the top of the wing here. You can see they're below 0 for most of that surface. And then on the bottom, we have a higher pressure. You can see they're greater than 0. This will result in a net upward force generating lift on our wing, which is what we expect. If we want to further verify that we're importing our pressures correctly, we can toggle on this Display Source Points option. When I toggle that on, it plots for me every point from our fluid analysis that we're reading results from. And you can see that it lines up well with the geometry that I'm looking at, meaning that our pressures are being imported properly. Now that we've defined our support and imported our pressure, all that's left is to solve the model. So I'm just going to right-click on Solution and hit Solve, and we will wait for this to solve. So now that our model's solved, we can take a look at how long that took. It looks like it's about 14 seconds. So now we can go ahead and start looking at some of our results. The first one we'll look at is the total deformation of the wing. So I'm going to navigate to that result there. And here we are, taking a look at the total deformation of our wing with this pressure load being applied. You can see the max displacement is a little over 1 inch. And you can see we have a scale factor being applied to this displacement to allow us to see the deformation a little bit better. We also have the undeformed model being plotted here for reference, just to help us see, how our wing is deforming relative to its undeformed shape. I can also animate this plot if I wish. Just another way to view this wing, just to make sure everything's behaving properly. So now that we've taken a look at our total deformation, we can look at some of the stresses in the wing. So I'm going to come to the stress result object here, and you can see the majority of the stress is at the base of the wing, which makes sense for an object in bending. I can also limit this stress result to be just specific geometry items of interest. For example, if I want to look at the stress on just the wing, I can scope it to just the skin of the wing here. You can see our stress profile is about the same, where the majority of our stress is towards the fixed support end of the wing, since it's in bending. I can also create a new one here if we want to look at just the stress on the ribs. So I'm just going to insert a new equivalent stress result. I already have a name selection set up for the ribs of the wing. So I'm just going to create this result now, and we can take a look at that. And you can see where our high stress areas are here. Finally, if we want, we can also take a look at the force reaction at the fixed support. So I'm just going to come to that result here. And this force reaction here tells us our lift and drag on the wing. So you can see, just based off of the directions here, that our X force reaction tells us the amount of drag on the wing. It's about 4 pounds. And our Y force reaction tells us the lift being generated by this pressure. This concludes this demo for a structural analysis on a ribbed wing in Ansys Mechanical. Thank you for watching.